Hey everyone, welcome to today's Explainer. For the next few minutes, I want you to think of me as your resident engineering professor. We're going to unpack a topic that's absolutely crucial to environmental science and sustainable engineering, water pollution. But look, we aren't just going to sit here and talk about the damage it causes. No, we're going to dig way deeper. We're going to look at water contamination through the rigorous, analytical lens of a civil engineer to figure out exactly where it comes from and, more importantly, how we actually fix it. Let's get into it.
So, when you picture water pollution, what do you see? I bet most of us instantly imagine this single rusting pipe, right? Just dumping this dark, murky sludge straight into a pristine river. It's a super powerful image, but honestly, it completely shatters the reality of how complex environmental contamination truly is. That single pipe, that's really just one face of a massive, multifaceted problem. Pollution actually comes from everywhere. Sometimes it's from those obvious sources, sure, but other times it's from millions of tiny, almost invisible sources spread out across entire landscapes. And understanding these different faces is literally step one in designing sustainable solutions.
Okay, let's quickly outline our learning objectives for today. First, we'll look at the two faces of pollution. Second, point versus non-point sources. Third, natural versus anthropogenic sources. Fourth, we'll tackle the core engineering challenge. And finally, we'll talk about analyzing your own local waters.
All right, Section 1, the two faces of pollution, understanding the where and the who. To solve any massive problem, you first have to categorize it. Not all surface water pollution is created equal. The contaminants that are clouding our rivers and lakes arrive there through wildly different pathways. By separating pollution into specific categories, engineers can completely transform their approach to treating it.
Moving right along to Section 2, point versus non-point sources, or the where of pollution. Now pay attention here, because this is perhaps the single most important distinction you need to understand in environmental engineering. This entire categorization focuses on one thing: whether or not a pollutant's origin can be isolated to one specific, identifiable location.
Let's start with point sources. These are basically the smoking guns of water pollution. Think back to that image of the leaky pipe we just talked about. If you can physically point your finger at a discharge pipe, say from a domestic sewage treatment plant or an industrial factory's wastewater outlet, boom, you are looking at a point source. They emit pollutants directly into the water body in a highly visible, incredibly identifiable way.
And sometimes these point sources are just absolutely catastrophic in scale. Take the 2010 Deepwater Horizon oil spill, for example. That single specific event released a staggering 134 million gallons of oil. To put that in perspective, that's enough to fill over 200 Olympic-sized swimming pools. It is the largest point source of oil pollution in U.S. history. But here is the critical silver lining of point sources. Because they are identifiable, they're controllable. You can measure exactly what's coming out of that pipe. And because of that, governments can regulate them using frameworks like the Clean Water Act, which sets strict legal limits on exactly what can be discharged.
Now, in stark contrast to that, we have non-point source pollution. And this is the invisible enemy. Instead of one leaky pipe, I want you to imagine 1,000 tiny leaks. This pollution comes from scattered, diffuse sources spread over massive areas. When rain falls and washes over the ground, it acts like a sponge, absorbing and assimilating whatever it touches, and then it delivers this incredibly complex cocktail of contaminants indirectly into our streams and lakes.
So what does this actually look like in the real world? Well, it looks like agricultural runoff, where rain sweeps across vast farm fields, carrying away fertilizers, pesticides, and animal waste. It looks like eroded soil and sediment just washing away from massive construction sites. And, of course, it looks like urban runoff, where rainwater flows over city streets and parking lots, picking up motor oil, heavy metals, and everyday trash. You literally can't trace this water back to a single pipe. It's an amalgamation of an entire landscape's footprint. The National Oceanic and Atmospheric Administration, NOAA, puts it pretty bluntly. They emphasize that non-point source pollution is incredibly difficult to control. And why is that? Well, because it originates from so many different overlapping human activities spread out across such a huge area. It presents an immense, systems-level headache for engineers and regulators alike. It's like trying to put a lid on a pot that's boiling over in 50 different places.
Okay, so just to lock this concept in before we move on. A point source is direct, it's identifiable, and it's localized, like a single leaky pipe. A non-point source is indirect, it's diffuse, and it's widespread, like 1,000 tiny leaks hidden all across a watershed.
Identifying exactly which one you are dealing with is step number 1 in any environmental engineering project.
That brings us to Section 3, natural versus anthropogenic sources, or the who of pollution. We've thoroughly covered the where, right? So now we need to look at the who. Like who or what is actually responsible for generating these contaminants in the first place? Now this usually prompts a really valid question. Wait a minute, can pollution actually be natural? We tend to think of pollution as this uniquely human invention. But in strict engineering terms, pollution is simply a harmful concentration of a substance in the water. That's it. And nature, all on its own, is completely capable of creating harmful concentrations without any human intervention whatsoever. Crazy, right?
A really prime example of this is a process called siltation. This is a baseline natural phenomenon where soil, sand, and minerals are naturally carried by water into streams and rivers. It happens every single day. However, and this is a crucial caveat, human activities like indiscriminate deforestation loosen the soil, and that allows floodwaters to wash massive amounts of silt from mountains into water bodies at a dangerously accelerated rate. So nature starts it, but humans put it in overdrive.
But beyond just siltation, even totally pristine environments have natural baselines of contamination. For instance, in super remote areas like the Tibetan Plateau, decomposing plants and microbial activity create natural organic matter that can actually contribute to the formation of contaminants like nitrosinamines. We also see the natural weathering of rocks containing minerals like fluorite and apatite, which can release really high concentrations of fluoride directly into the groundwater. And of course, natural disasters like wildfires and floods sweep massive amounts of debris into our water systems. As engineers, we must rigorously account for this natural baseline, especially when we're treating groundwater for human consumption.
But then we have the anthropogenic sources. This is the human footprint. These are the man-made activities responsible for the vast majority of the severe acute water pollution problems we face today. We're talking about millions of gallons of domestic wastewater pouring from our sprawling cities. We're talking about industrial wastewater laden with chemicals, heavy metals, and thermal pollution. And we are talking about immense, staggering volumes of agricultural wastes.
And the sheer scale of this anthropogenic impact? It's just staggering. Take the Yangtze River Basin, for example. In just a 16-year window, from 1998 to 2014, municipal wastewater discharge jumped from 2,580 cubic meters per second all the way up to 3,646 cubic meters per second. That is a massive, massive increase in man-made pollution entering one of the world's major waterways, really highlighting the rapidly growing burden of human activity.
All right, Section 4, the engineering challenge, where categorization is key. So we have the where and the who. But why does this academic categorization actually matter in the real world? Well, for environmental engineers, properly categorizing the problem is quite literally the only way to design the right solution. The category you're dealing with dictates your entire engineering approach.
Let me explain. If an engineer is looking at a point source, that single industrial pipe, the solution is going to be highly localized and very technological. You design a focused treatment facility right at the source, utilizing advanced membrane filtration, complex chemical processes, or biological reactors. But if you are tackling a non-point source, like that diffuse agricultural runoff we talked about, a high-tech filter just isn't going to work because there is literally no single pipe to attach it to. Instead, you have to design landscape-scale green infrastructure. You build constructed wetlands to naturally filter the water over large areas. You implement buffer strips along riverbanks. And you design permeable pavements for urban cities to absorb the runoff before it ever even reaches the river.
Now, while it's up to state or central governments to handle the administration side of things and set the legal standards for water quality, it's the engineers who actually have to execute the solutions. And today, we are using incredibly advanced tools to do it. For example, in the Hanjiang River Basin, engineers are actively deploying machine learning and complex data-driven models to track and pinpoint these elusive pollution sources with a level of precision that was honestly completely impossible just a few years ago. It's a real game changer. Finally, Section 5, analyzing your local waters, or the bigger picture. As we wrap up this explainer today, I want to pull back a bit. We've covered a lot of rigorous structural concepts, but I want to stress that these aren't just textbook theories. These are the actual tools we use to literally change the physical world around us.
So, the absolutely crucial takeaway here is that this workflow is the foundational roadmap for professional environmental design. Step 1, you locate the pollution and classify it as point or non-point. Step 2, you identify the origin to see if it's natural or anthropogenic. And finally, step 3. You use all that data to either design focused technology for the pipes or expansive green infrastructure for the landscapes.
I want to leave you guys with a bit of a challenge today. Call it a homework assignment, if you will. Next time you walk past your local river, a nearby lake, or even just a community pond, I really want you to look at it through the eyes of an engineer. Look around the landscape. Are there factories nearby? Farm fields? Stormwater drains? Try to identify the true sources of any contamination you might see. Is it a point source that you could fix with a focused treatment plant, or a non-point source that requires entirely redesigning the landscape? The answers might genuinely surprise you. Thank you so much for joining me for this explainer, and remember to keep asking the hard questions about the world around you.